Hello everyone, my name is Brian Kang from Charochi High School. Today, I'm very excited to present my project titled Dynamic Early Decision Model for Reducing Latency in Non-Invasive Brain-Computer Interfaces. I know this title sounds very complex at first, so today I'll clearly explain what the problem is and how I was able to solve it. Around the globe, millions of people worldwide are affected by stroke, a spinal cord injury, and ALS. Non-invasive brain-computer interfaces allow these users to control devices directly using brain signals such as robotic arms. However, the biggest limitation of this technology is delay, and that is why in this project I focused on reducing that delay. This slide shows a general table of major patient groups who may benefit from non-invasive BCIs. If you look at the figures, you see numbers like 80 million, 17 million, and 69 million, showing you how many millions of lives could be affected, or benefited from faster BCIs. Now let's move on to the methodology. The core idea of this project is very simple. Instead of waiting for the entire EEG signal, I asked whether movement intention appears early in the signal. If intentions appear early, the system can react earlier. This gives us a direct way to reduce delay without using invasive implants. Here are the four main steps of the overview. First, we input data. 2, we create a base model. 3, full window benchmark verification is needed. And lastly, we create a dynamic early decision model, which is the full main core of the idea. I will go through these steps more specifically on the next slide. This slide covers step 1 and step 2. For step 1, data input, I use PhysioNet EEG motor movement dataset, which includes 64 EEG channels, 109 human subjects, and 4,813 real movement trials. This confirms that the model was trained on real human EEG data. For step 2, I built a baseline deep learning model using CNN LSTM architecture. And how it works is shown in figure 2. The model works in two parts. 1, the CNN finds short patterns in multiple EEG signals, and 2, the long short-term memory then learns how these patterns change over time. And after repeated process, the model learns to distinguish the rest from exact movement that we want to know. Now, in step 3, the full window benchmark, the baseline model we just created waits for an entire 2-second EEG signal before making a decision. This gives the highest accuracy, but the slowest response at the same time. Please remember that this benchmark testing was done to allow us fairly compare performance later on. Now, in step 4, final production, the dynamic early decision model, the system checks the EEG signal as it arrives from the start. As is shown in figure A and figure B, instead of using the full EEG signal, the decision window slides forward continuously, checking for confidence levels. And when this confidence level passes 90%, the model immediately makes a prediction, and this is how delay is reduced. Now, let's look at the results, because it was truly remarkable. For the full window benchmark, aka step 3, the model reached 78.29% accuracy. This might seem insignificant at first hand, but this is a very strong performance for a noisy, real EEG dataset. For comparison, a PubMed indexed, published model called EEGNet only reached about 82.43% on the same dataset I used. This confirms that our baseline model was reliable. But keep that in mind that this was not even our main goal. Our main focus was reducing latency. So now let's look at the latency reduction. After 4,813 trials, the dynamic early decision model made predictions much earlier on average. The average prediction time was 0.592 seconds compared to a full 2-second window benchmark. This is a whopping 70.4% reduction rate in latency. Even more importantly, the model preserved 95.29% of the baseline accuracy. This means that we reduced most of the delay while keeping nearly all of the accuracies. To summarize, this project asks one main question. Can we truly reduce delay in non-invasive BCIs while giving up only small parts of accuracy? The answer is yes. Of course, there are still limitations. First, the study used pre-recorded EEG datasets instead of real live signals. Second, more importantly, the model was tested only in software and not yet on real hardware. And that is exactly why my future work focuses on real-time testing with robotic arms. But I want to be very clear about one thing. This is not just a list of future ideas, as I've already created a robotic arm that will be connected to the live EEG signals and is currently on testing. Thank you for listening, and this was Brian Kang.